So today we'll look at serializability, okay, and we will determine how to figure out when a schedule is serializable, okay. By default, serial schedules are always serializable, but whenever instructions of transactions are interleaved, it is harder to determine whether a schedule is serializable or not, okay. The basic assumption that we are making also is the fact that each transaction that is designed by a programmer necessarily has to preserve database consistency. Okay. Once every transaction preserves database consistency, the DBMS can look at consistency across concurrent execution of transactions. Okay. So we just said this serial execution of a set of transactions always will preserve its database consistency. Okay. The other assumptions that we're making is that operations other than read and write instructions are ignored. We have seen this in the previous schedules that we looked at. We only looked at the read and write operations. And transactions may perform arbitrary computations on data in local buffers in between the reads and writes. Okay. Thus, for significant operations of a transaction from the point of view of scheduling are only the read and write instructions. All the commits and aborts are there, but for the point of view of scheduling, initially, we will only look at reads and writes. Later on, we will see what happens when commits and aborts are there in the instructions. Okay. A possibly concurrent schedule is serializable if it is equivalent to a serial schedule. Okay. And there are various forms on which we can look at equivalence of schedules, but what we will focus on today is conflict serializability. And once we've understood conflict serializability, we will look at view serializability. Okay. Okay, so consider a schedule S in which there are two consecutive instructions, which we are calling II and IJ. And II will belong to transaction TI, and IJ will be an instruction from transaction TJ. And obviously, I is not equal to J. Okay. If II and IJ refer to different data items, then the order of these are not really important. So we can swap them without affecting the results of any instructions in the schedule. Okay. However, if I and J refer to the same data item Q, then the order of the two steps are going to matter. Okay. So another point we need to look at is instructions II and IJ are said to conflict if there exists some item Q accessed by both II and IJ, and at least one of these instructions did a write on Q. Because we know that when we are doing a read on Q, even if we have multiple instructions reading the data item, there is no problem. There is no conflict, right? Because multiple instructions could read the same data item and it will not affect how many are going to be reading that data item. Okay, it does not affect the other transactions that are reading the data item. However, if one of them has a write on the data item, then there is a conflict between the others. Because if one does a write and the other does a read, the time in which the read has been done will differ. Okay. I mean, the value that the read of that data item is being read off will differ whether the write has already been done or the write has not been done. So there is a conflict. Okay. So this is what we look at, whether there's a conflict or not. So if II does a read on the data item Q and IJ also is reading a data item Q, they don't conflict. Okay. And because they don't conflict, the order in which they do the read does not matter. Okay. But if II does a read on Q and IJ is another transaction instruction that does a write on Q, they conflict because the order matters. Because if II did a read after IJ did a write, then the value that I will read will be different. Okay, will be different from what it would have been if it was read before IJ did a write. Okay. Similarly, if II does a write and IJ read by the same argument, they conflict. Okay. Now, similarly, II, if does a write on Q and IJ does a write on Q, also they conflict. But they conflict because the next instruction that does the read on the data item will get the read of the last updated data item. So whether it was I doing the write or IJ doing the write, whichever was the latter updated write would be the one that was read by the next transaction. Okay. So these orders differ and they conflict whenever there is a write operation. Okay. So this is what we need to understand. Let's carry on. So let's read the next statement. Intuitively, a conflict between II and IJ will force a logical temporal order between them. By temporal, we mean time. So when the particular operation is read or written onto, there will be a difference in what it has read. Okay. If II and IJ are consecutive in a schedule and they do not conflict, their results would remain the same even if they had been interchanged in the schedule. Okay, so that's a point we need to remember. Okay, so let's look at this in slightly more detail. If II is a transaction from TI that does a read queue, and IJ is a transaction from TJ that's doing a write queue, then if II comes before IJ, so we're looking at an instruction II that comes before transaction instruction IJ. Okay, this is done by transaction TI and this is done by transaction TJ. Okay, then TI does not read the value of Q that is written by TJ in instruction IJ. So II is doing a read. Okay, and IJ is doing a write. So II, since it comes before IJ and the write has not yet been written, then the transaction TI is basically reading from the database. Okay, not the updated value. This is the read that is being done. Okay, let's look at the next statement. If IJ comes before II, so we're looking at the next case. If IJ comes before II, okay, IJ is from transaction TJ and II is from transaction TI. Okay, then since II is doing a read and IJ is doing a write, then transaction TI is basically reading the value that was written by TJ. Okay. And in this case, the order of II and IJ matters because they're reading different values if they come at a different time. Okay. So the ordering matters. So that's what this statement is telling us. When the conflicts will come in, this is what is going to happen. Okay. In the same way, the same argument that we did above, if II is doing a write queue and IJ is doing a read queue, the order matters, correct? Because it will differ to which is the read that is being done by instruction IJ. Okay, whether transaction TJ is going to be reading the value from the database or reading the value that has been updated by transaction TI, the ordering will naturally matter. Okay. Now let's go for the third case, because the case where both of them are doing a reads does not really cause a conflict. Okay, only when one of them is doing a write, there is a conflict in the database, right? And what is going to be the output? Okay. Now, even in this particular case, if I is doing a write and IJ is doing a write, although both of them are doing a write and there is no read operation over there, there is a conflict because what happens is the order of these instructions does not affect either TI or TJ, but it affects the next instruction that is going to be reading it. The next transaction that comes into the system and reads the value of Q, it will read either II's updated value of Q or IJ's updated value of Q, depending on which is the last updated value. Okay. So the ordering matters and there is a conflict. So that's what it says. However, the value obtained by the next read queue instruction of S, that is a schedule, is affected since the result of only the latter of the two write instructions is preserved in the database. The other one gets overwritten by the last write operation. We saw how that takes place, right, in the previous, schedule, which led to inconsistency. Okay. If there is no other write queue instructions after II and ij and s, then the order of II and ij directly affects the final value of q in the database state that results from the schedule s. Okay, that's what we are saying. Okay, what we've just said. So let's look at this and see what happens when we have this conflict serializability. Okay, now if we look at these instructions, we have come across a schedule that more or less looks like this. But let's see if this is conflict serializable. That is, can we create a serial schedule from this set of interleaved instructions? So how do we create a serial schedule, or at least try to create a serial schedule? If we can interchange or swap these instructions, okay? If they do not conflict and we end up getting a serial schedule, then we say that this particular schedule is conflict serializable. Okay. So there's a read here and a write here, but it's within the same instruction. So we're looking at different transactions. So we come across this particular transaction here. There is a write A in schedule 3, and there is a read A in transaction T2 in the schedule 3 itself, right? So there is a conflict over here, and we can specify that there is a conflict. Because there's a conflict there, we cannot swap these instructions. But let's look further, okay? If we look at a write A from transaction T2 and a read B, there is no conflict because they're two different data items, right? So there's two different data items that do not conflict between those, and we can swap the order. That is no problem. So once we swap the order of this, that means we take read B before write A at this particular point in time. Okay, we end up with a swapping constructions, and we end up with this. Okay, we're taking this above the write A. Okay, so now when we look at this particular schedule, which we're calling schedule 5, we try to see where else there is no conflict. Okay, there is no conflict between write B and write A, correct? So we can look at this. So since write B of transaction T1 with the write A of transaction T2 do not conflict, we can swap these instructions, right? So we can take this write B above here, and we end up with this particular schedule over here, okay? With this schedule that is here. Now, if we look at this particular schedule again, we try to find if there are any conflicts that are available, okay? If there are particular conflicts that are there, and we find that there is no conflict between write B and write A again over here. So we can take this above here, and now we have write B at this location that is here, okay? Then we have write B and we have write A over here. There is, we have read A over here. There is no conflict because T2 is doing a read on A and T1 is doing a write on B. So we can move this still further up here, okay? So we can swap these instructions and we end up with a serial schedule, okay? So this is the schedule we end up getting, okay? Now, let's go back to the previous page. We had a read A, write A, read B, write B of transaction T1, all before transaction T2 execution, right? So we end up with a serial schedule, which makes this schedule conflict serializable, okay? Because we have produced an equivalent serial schedule of the previous transactions, okay? So schedule that were there, okay? So this actually stemmed from this previous schedule that we had looked at, which we had called schedule 3. And we said that whatever instructions are done in between, we really don't matter. We're only interested in the reads and the write. So the previous schedule that we had over here, the schedule 3 that we had here, was actually this schedule that we have without the intermediate operations that are here. Okay, and we converted this schedule into a schedule 6, which is called a serially equivalent schedule. Okay, so we have a conflict serializable schedule from schedule 3, and we made it into an equivalent serial schedule, which we called schedule 6. Okay, these are just schedule 1, schedule 2 are just something that we just named so that we can identify the schedule. Okay. This is the next statement we make. If a schedule S can be transformed into a schedule S dash by a series of swaps of non-conflicting instructions, we say that S and S dash are conflict equivalent, right? So in the previous case, we had an equivalent conflict I should say we have a conflict equivalent serial schedule, okay? So we say that a schedule S is conflict serializable if it is conflict equivalent to a serial schedule. So that's what we created, a serial schedule, which we call schedule 6. Let's look at this particular schedule, and it says it is not conflict serializable. So let's see why it is not conflict serializable. So if we look at read queue here and a write queue here, we cannot do any swapping of this because there is a conflict. Similarly, if we do a look at this, there's a conflict between this write queue and this write queue, correct? So wherever there is a write, we end up having a conflict. So T3 has a read queue, which is before T4's write queue, so we cannot swap. Similarly, T4's write queue has a T3 write queue, which again we cannot swap, okay? So it is not conflict serializable because we cannot come up with an equivalent serial schedule, okay? So we are unable to swap instructions in the above schedule to obtain either the serial schedule T3 followed by T4 or the serial schedule T4 followed by T3, okay? There is another way or a simpler way of testing for serializability is via a graph and to see whether we can, if there is a cycle in a graph, okay? So consider some schedule of a set of transactions, T1, T2 up to Tn. We call a precedence graph, which is a directed graph where the vertices are the transaction names, okay? We draw an arc or an edge from Ti to Tj if the two transactions conflict and Ti access the data item on which the conflict arose earlier, okay? So Ti has to access the data item before Tj to have an edge from Ti to Tj, okay? We can label the arc by the item that was accessed. So this is an example of a graph of the transactions that we just looked at earlier. T1 to T2. Let's draw that graph over here. We'll draw it on the same slide over here. We have a conflict from T3 to T4. So we'll have T3 to T4. There is a precedence because T3 accessed the data item before T4 on Q, okay? And T4 also to T3, there is a graph because the precedence of T4 is instruction that has a write queue prior to T3. So on the same data item, so it doesn't matter, right? So we end up with a cycle in the graph. So we can say that it is not conflict serializable, okay? So this is for two data items, which we could look at as A and B. Maybe it arose from schedule earlier schedules that we had. So let's look at one of the earlier schedules and see what kind of a graph we get from that, okay? So let's look at a schedule that was not consistent, okay? These there are no problem because we'll only have, since T2 accesses it first, we'll have a graph from T2, we'll have a to T1, sorry, to T1, okay? Here what happens? We have a graph. Since we are doing a relay, we have a graph from T1, an arc from T1 to T2, okay, on data item A, because it accesses it prior. And then we have an arc from T1 to T2 again on data item B. So if you notice that there is no cycle in this graph, and therefore it can be considered to be serializable, conflict serializable. And we did find an equivalent schedule, okay? Let's look at any schedule that we had that does not give us. Let's look at this one, okay? We have an arc from T1 to T2 on data item A, right? Because we have an A here and an A here, right? Now we have a read B here. So we have T2 is doing the read before T1 is doing the write. So we have this on B. So if you notice, there is a cycle on this graph on the data items, and it is not, okay, it is not serializable. Right? And we proved that it is not serializable, and we proved that there was inconsistency in our schedule. If we kept the schedule, there would have been an inconsistency in our database. Okay, so we don't want the schedule. Okay. So this is what we looked at. Let's look at another example, maybe. Okay. So there's another example here, and we need to check whether this is conflict serializable. So if you're more in, if you look at the way we have been writing it, so we'll continue with the same way. Read A, write A, then we have read A, write A, read B, write B, okay, and then we have read B, write B. Remember, we said that if they have a different, if they look at database items and they're trying to read database items from different sources, we end up saying that it is inconsistent. So we do have inconsistency here, because if you notice, the transaction T1 is doing a read and write of A from the database, but it is doing a read and write of B from the updated items of transaction T2. Okay, so this one is T1 and this one is T2. So let's draw a precedence graph. Since we have conflict over here, I'll just draw the thing here. So I'll write it T1, T2. We have conflict here. So we draw a graph here on the database item. And we have a problem here also. So we have a graph here, an arc here for the graph on database item D. So we know that that is a cycle in the graph, so that it is not conflict serializable. Okay. Right. So those are the answers here. Let's look at this one and check to see whether it is conflict serializable. Okay. So if we have T1 here, this read and this read do not conflict. So we do not have an arc from there. But this, similarly, this read and this read do not conflict, but there's no problem. But we have a read here and a write here. So they conflict here. We have a write here and a write here. Okay, so it conflicts here. So the graph that we end up having is this. So T1 to T3 on the data item X because of the read X and the write X here. T3 to T1 on database item X because there is a write of the two over here. We also have a write X here and a read X here, so it conflicts over here. So between T3 and T2, there also is an arc. And between T1 and T2, we don't really need to keep that arc because it's a read on the database items. Okay. So what we need to look at over here is, since this is only a precedence graph, we can retain that. But when we're looking at a cycle, we find that there is a cycle. Okay. So it is not conflict serializable. Okay, we'll look at view serializability in the next session.